Good morning. So we are going to now continue with the last class from where we left. And in the last class, essentially, we were able to understand the dynamics of space vehicle. That means vehicle which is not on the ground. You see an aircraft or the future flying car, hybrid mode vehicle which can run on the road or can fly on the sky. So the dynamics of them, the governing equation of them is what essentially in the last class we have seen and we derived. So there are essentially six equations. There are three force equations in XYZ direction, the three components of the resultant force at the CG location of the vehicle. And there are three moment equations, again resolved along XYZ direction. And these are essentially going to get involved in control of 6 degrees of freedom. That's forward motion of your vehicle in space or its ascent or descent in a vertical direction called the heave motion in aerospace technology. You would see them. That's called the heave motion. Or it is the motion in a lateral direction when there is navigation on a right or left it's going. So these are the three motion velocities that are essentially there in a space vehicle in translational responses. And the other three are the rotational responses. What are those? The rotation about your forward axis, x-axis. So that's called the roll motion of your aircraft. And the other two motions are the pitch motion along the lateral axis, and the yaw motion, that is the change of orientation when you see from the top your vehicle, right? So these are the 6 degrees of freedom essentially required to have no collaborative understanding about themselves to have a stable and safe motion of your vehicle in the space. And of course, these forces and moments are generated by the prime mover and the design of your vehicle, and they are able to withstand against any poor atmospheric conditions and so on. So the safety of the vehicles have been much ensured. We were aware of them. So with that background, we have essentially looked at an interesting aspect of the dynamics, just to deriving the six governing equation, and those are essentially called as a name Newton-Euler equations, right? So that's what we have done. Of course, our course is not the spacecraft dynamics, aircraft dynamics. Our course is vehicle dynamics of vehicle on ground vehicle confining to two-axle vehicle. That's essentially a passenger car. So if that is so, how can I make use of those six equations for the dynamics of passenger car? Is what is essentially is the starting point for us today's class, and we are going to deduce those six equations conveniently with an appropriate assumption, which are very sensible and valid assumptions. And the equations will be very simple and no, it's not like a very lengthy equation what we have seen in the last class at the end. Are very simple and very easy to handle. So handleable equations that we are going to get, which can be worked on the board or in your notebook, and you can solve some problems. And I say some problems means that model is quite sufficient model to study a huge spectrum of your vehicle dynamics, particularly lateral dynamic aspect. That's the beauty of that equation that today we are going to deduce and see. So what I mean by that, the main objective of lateral dynamics is your directional control and stability of your vehicle is what we have started in the last class stating at the beginning. And that could be well studied with the simplified simple equations. That's what you'll understand at the end of this class. And the model description to study the directional response and the stability analysis of your vehicle with the governing equations. So, or by basic kinematics and the model description, and possibly the governing equation reduced to a state space form. Time permits, I would go till there. Otherwise, I will stop by kinematics and description of model, and then we will proceed further. So, this is what essentially we are going to study in this one particular period. I'm going to share now my screen and to start the lecture. So, hope you are able to see this. Let's look at what we did in the last class. It's not visible at the moment. Let me put this for benefit. So we were just doing this essentially. I'm not going to go again in detail. You know that yesterday what we did. We looked at this aircraft and we were essentially used two-axis system. One is an initial frame of reference, which is this axis capital X, OX, OY, YZ axis fixed on the ground, which is non-accelerating, non-rotating axis, right? And then another axis system is what is called a body fixed coordinate system, fixed at the CG location of your aircraft, and that essentially has got to describe its velocity, acceleration, or any vector that's attached to that, for that matter, force and moment vector. And these are the axis system coordinate, and that is the rectangular coordinate axis system, or you can say Cartesian coordinate system, fixed in the body where you have your right hand, three fingers are stretched in this fashion. The index shows the forward direction X, the middle finger shows the lateral direction, and the thumb shows the downward direction. These are positive directions. This is essentially the axis system we are going to look at in our ground vehicle as well for lateral dynamics study. And here body coordinate system demerit means the position of this aircraft at any point of time you cannot define with respect to body coordinate system. But why do we consider that is because this aircraft, when we are coming out of our particle ideology, I need to look at this all 6 degrees of freedom. So the velocity of your aircraft and the rotational velocity of your aircraft to be best described with respect to its own fixed coordinate system. And that variation, because this axis is now, as this motion requirement, is going to have an acceleration, rotation. So the coordinate fixed here is non-inertial frame of reference. So there we can best describe your velocities or force and moments. And then you would be able to look at the variation of velocity from the ground, from inertial frame of reference, to get an acceleration. And that would also account your rotational effect of your aircraft. And essentially, you are able to derive your acceleration, and then you have your force equation. You are able to derive your angular acceleration. You are able to have your moment equation. That's what is the crux and the basic dynamics of them. And essentially, by principle of linear momentum and angular momentum that we have seen. So the force is rate of change of linear momentum. The momentum, the moment is the rate of change of angular momentum. So in that process, we defined the angular momentum. That's also a vector, but it is going to be dictated by the centroidal inertia matrix. You have these 9 elements, and all 9 elements do exist for an arbitrary shape of the vehicle. If it is like an aircraft, you see that symmetry about XZ plane. So you would have 6 components and so on. So you have mass moment of inertia, which are diagonal terms, and you have product of inertia, which are off diagonal terms. So their influence is there for your moment, whereas for your force, that's only one that comes from the mass of your total mass of your vehicle. And this is what essentially we understood. The derivative of a vector in body coordinate system, the vector which is accelerating and rotating about a body coordinate system, and its absolute value with respect to inertial frame of reference would be obtained by this relative derivative plus the effect of rotational motion of your axis system. So that's essentially we understood, and we applied that, and then we were able to derive equation 17 and equation 19 and the equation 18. So 17 and 18 are called the Newton-Euler equations for this 6 degrees of freedom vehicle in space. So what we needed is so far not for essentially ground vehicle. So we are going to do it now as a starting point in this today's class. So today's class, this lecture number is 19. Let me just write this is lecture 19. Today's date is 27/09/2021. So what is that you're going to look at today is you're going to deduce the 6 equations, required numbers for your ground vehicle. So I'm going to do lateral dynamics of ground vehicle. vehicle, particularly passenger car. Right? So this is what we're going to study. So let's look at now how this equation can be simplified further, right? So let's look at this equation, Newton-Euler equation. So here you have three force equations. So F is equal to m into this, Fy is equal to m into this entire thing, and Fz is equal to w dot m into w within bracket w dot plus pv minus qu, right? So the equation. Similarly, you have three moment equation. So for that matter, these six equations are for the rigid body, very generic, not even for an aircraft. You don't require for an aircraft what we have considered and derived. These are all six equations in this full form, like this. You require six equations, but that would appear again as a simplified form. So what is that? Look at here, you have you have this aircraft. So this aircraft structure is symmetry about which plane? If I ask you, you would say that it is symmetry about XZ plane. So the moment you say the symmetry comes into picture for a rigid body, for a vehicle, this mass moment of inertia term becomes simplified. So other than XZ term, you have rest of them only exist, the others would be zero. So IXZ is going to be zero because it's symmetry plane, and you have only IXY and you would only have IXZ and you would have IXY or IYX or IYZ or IZY is equal to zero. So let me have from this. So from Newton-Euler equation derived. Case 1, what is that I'm going to consider is if X is at plane is symmetry like an aircraft, right? Then what would happen? I would have this IXY equals IYZ, the IYX equals IYZ equals IZY equals 0. So these all terms are going to be 0. So I would have essentially only IXZ, IZX, so the same value, and four mass moment of inertia terms, diagonal terms. So then what would happen? My equation would be further simplified, right? So I would have my three force equation, of course, and I would have my moment equation would be simplified as these terms are going to be zero accordingly. So I leave it to you to as a homework and to see those simplified equation, right? So this is again what symmetry, even the same six equation for an aircraft. We have not come to a ground vehicle yet. So what is that for a ground vehicle? Let's call that as case 2 as for ground vehicles. What is that passenger car you look at? We have studied before lateral dynamics, the vertical dynamics. So there we have considered quarter car model. Why do we consider quarter car model? Because it is an identical part of a full car, and you are able to study that mathematical model for your bounce motion of your vehicle vibrational model. So when your vehicle is identical as four parts, what does that essentially means? You have your X, Y, Z axis or principal axis. Principal axis. So you know what are principal axis? The principal axis are the one where you have product of inertia zero. Therefore, all terms of product of inertia zero in IC matrix. So what is IC? Inertia, centroidal inertial matrix. So I'll have only mass moment of inertia, that is diagonal terms. So that's what is interesting, right? supposing if that is not an identical part, I have my rear of the vehicle is different and front of the vehicle is different, like a hatchback vehicle and so on, then what will happen? I'll have my symmetry alone. So if I consider like here the symmetry alone, if I consider here, so this is one assumption posed for the vehicle principal axis. Another assumption before that, let's have XZ plane symmetry. That should have been first and then this should have been introduced. Anyhow, this XYZ plane, XZ plane symmetry is similar to aircraft in a passenger car. If I consider what are the governing equation, if you look at, I would have only 4 equations, and those are Fx equals mass into U dot minus RV, and Fy equals M into V dot minus RU, and there is no FZ equation. Let us see why. And then Mx is going to be Ixx P dot plus Ixz R dot, and Mz equals Izx P dot plus Izz R dot, Izz R dot. So these equations for ground vehicle, there are 4 equations. There are 6 equations here. With these 4 terms are 0, you'll have 6 equations here for simplified equation for aircraft. But the moment it is a ground vehicle and I have my vehicle is XZ symmetry, what I mean by that is here, these all 4 terms are 0. That's one assumption here. That's valid. Now Ix is there. Xy is equal to Iyx is equal to Iz y is equal to Iyz, all 0. That's one. And additionally, since it is a ground vehicle, not a flying vehicle, I would not require to consider the heave motion. What is here is called the heave motion. So heave motion is what is in vertical direction. The aircraft is ascending up or descending down. So that is what is heave motion, and that is not going to be there in your ground vehicle because your ground vehicle on the ground. So I would neglect my heave motion, so the W term won't be there. That's why there is no FZ term. Of course, FZ is there. That is the load of your vehicle, and that would be balanced by your normals, the contact patch of your tire road interaction. So there is no W motion. So W motion, and similarly, there won't be any pitch motion. So Q and Q. So you know omega equals PQR vector, right? Where omega column vector represent your angular velocity of vehicle has got these 3 motions. P refer to roll motion, Q refer to pitch motion, R refer to yaw motion. So in a ground vehicle, you have a pitch motion. Why? Because there can be load transfer. Because in a vehicle, there you have a suspension, so your mass, total mass is discretized as unsprung mass and sprung mass. So there can be load transfer during your action of braking or action of accelerating. So when you're accelerating, you have load from front to the rear goes. When you're braking, suddenly the load comes back to the front. That's why we fall forward during braking, right? So that load transfer is there. So the pitch motion essentially to be there, you cannot neglect it. And as you drive your vehicle, you don't go straight, you have to maneuver, then you require orientation change. That is why yaw rate is present. Whereas Q is what is pitch here. And that is not, you may ask why pitch can be neglected. So pitch motion, essentially in aircraft, it is when you go up, right? When you are navigating, that is the motion. That motion is neglected in this context of a ground vehicle. Particularly, we are going to consider for a moment, it's a rigid vehicle. I will not consider my suspension. So when I will not consider my suspension, you cannot discretize your vehicle mass as unsprung and sprung mass. I'll take all as a single mass and consider. So there won't be any pitch. There will be no roll. There will be no lateral. All these are not going to be there. It's only translation, you can say. But still, it's valid to have roll and your raw. Yeah, because I want my ground vehicle degrees of freedom reduced to 4 from 6. 4 degrees of freedom. So what are the 4 degrees of freedom? Are now two translation, forward motion, there's a lateral motion, and then you have two angular velocities. So W and Q can be neglected with the plane of symmetry assumption. This and this is my second part. So if I do this all, my equation reduces to this 4 numbers. The 6 equations reduces to 4 numbers, and this is quite sufficient to study your control as well as stability. So why do I have to consider my role, you may ask? Why do I have to consider my role? Is because rollover stability to consider, I require my P dot. So stability analysis to consider. And R, why is it required? Because it has to change its orientation. So R motion is important. So these are the 4 motions, quite sufficient, 4 degrees of freedom. And these are the 4 governing equation for the ground vehicle. Right? But we are not going to start straight away with these all 4 equations. Further, we are going to simplify and to start our lateral dynamic study. So what are those? That's case 3 now. Case 3. So case 3 for lateral dynamics of ground vehicle, I'll consider now this principle. In case 3, this X, Y, Z directions are principal axis. Along with this, the W and Q neglected. So whatever that I was telling, this is now applicable. I'm introducing this assumption at the moment now for the third case. So the case 2 is 6 degrees of freedom reduces to 4 degrees of freedom because of this plane symmetry, and neglecting the 2 degrees of freedom, that is vehicle is on ground, and pitch motion I don't consider. That means the pitch motion I don't consider means it is necessary to consider, but we can unless until it is the right dynamics part, it is not needed. My vehicle is not going to go on a road like front hitting, back hitting, like that I'm not going to ride. In a steady state, or whenever I go straight or take a 2D motion, the steering input when I give, I don't get my vehicle pitching and going. The load transfer is not going to be like that unless and until you go slow and over a bump you go, that time only it is there. Otherwise, you go in a cruising speed, called a steady state motion of a vehicle, you don't see this pronounced, this Q. That's why we neglect it. And of course, the W is not there. You should not misunderstand what is bounce motion with this. Bounce motion is a local motion in your vehicle, right? So that is to study your vertical dynamics alone. But that does not make your vehicle coming out of the ground. The ground has always been in contact with your vehicle. The vehicle has always been in contact with the ground because of your suspension system. So there is essential tire dynamic deflection there to be present, and so on we have studied. So these 2 motions are neglected. That has brought down the 6 from 6 4 equation, and the symmetry of XZ plane further is reduced this form, right? Okay, so now further, if I consider this symmetry along with the 3 principal axes, what would happen? I would have my IZX term also 0, right? IZX term also 0. IZX is equal to IXZ also 0. Because all 3 axes are principal axes, I will have only mass moment of inertia or the diagonal terms in my inertial centroidal inertial matrix. So these 2 terms would disappear, and I would have my equation now reduces to this. So I will have now Fx equals m into u dot minus r v, and Fy equals m into v dot minus r plus ru. So these 2, and I would not require now this x equation. Why I don't require this x equation, mx equation, is because I don't want to consider now the roll motion as well. So here neglecting the roll along with this assumption, neglecting the roll motion. Why neglecting the roll motion? If I have, as long as I have a suspension, you would have a sprung and unsprung mass. If I do not have suspension, I consider this entire vehicle as one rigid body. Even this roll motion would be neglected. And that would be when it is required, this when I have to go for rollover stability and so on. But at the moment, I can even make this assumption, roll is neglected. So I have my 3 degree of freedom model now. So here I would have my forward velocity, I would have my lateral velocity, and of course I will have now only mx. I do not mz. I do not require mx because roll is neglected. Mx is disappearing. So mz is equal to, and izx is 0. So this term won't be there. It's only izz r dot. So these are the three equations, sufficient equations for ground vehicle study when I do not consider suspension. When I don't consider roll, when I say no roll, no pitch, what I mean by that, there is no flexing action of a body of a vehicle with reference to unsprung mass. So suspension is not there. So if the suspension is not there, you would not have these motions, right? What are the motions? They are not there. You do not have roll that's given by P. Roll rate is not there. So roll motion is not there. And you do not have pitch, that's Q. So the pitch and roll effect is disappear the moment no suspension considered. So you may wonder and ask question, without considering suspension, how can I have my dynamics? So what is the objective of our lateral dynamics? Lateral dynamics is to study is my vehicle has got a directional control and stability in the plane. That's called the yaw plane stability. So the main objective of your lateral dynamics is directional control, and another one is yaw plane stability. So what I mean by yaw plane stability, it is X is that plane. So if this is my vehicle, this is my vehicle, right? This is my vehicle. So I require only the directional control and yaw plane. So if I take a turn here in the top view, I should see that my vehicle. So two front axles are independent suspension. So yes, solid axle suspension. So if this is turning, so I require only the yaw motion. So the vehicle, as long as on the ground and it is stable, that it takes a turn. So when I drive my vehicle and I go high speed and then I suddenly have to take a turn and I see that I need to brake, or I go straight and I brake. Sometimes what will happen, this vehicle orientation like this, the front and rear end, won't be there. So the rear of the vehicle comes front and front comes rear. There is a spinning action of your vehicle. That's what is called an unstable motion of a vehicle in yaw plane. So yaw plane essentially is the ground plane, right? So in the ground plane, is your vehicle is stable. So when you say vehicle is stable, when the direction of the vehicle controlled. So it is going straight when it is needed, when it is taking a turn when it is needed, and the orientation of the orientation. When I say from top view, the vehicle orientation, that means front axle in the front and rear axle in the rear. Orientation is correct. So then it is going to change its orientation, and then it is going to have adopt its motion according to the way the driver wants the vehicle to move. So that is what is ensured. That is what is called the yaw plane motion. At that time, I don't worry about the rollover of unstable state. That's of course there for a high vehicle, buses and double decker. You see, you can't drive the vehicle with the high speeds. So there is a very easy chance of getting pronounced to rollover problem. So when you drive a vehicle on the highways and side wind so strong, it can make a vehicle to topple. So that's going out of the ground. That's called rollover stability. At that time, you have to consider your suspension and so on. So we will consider that separately as a roll dynamics later in our lecture. At the moment, I am not going to look at it. So my primary objective of lateral dynamics, main objective of lateral dynamics is directional control on the ground and yaw plane stability. Then these three equations are quite sufficient equations. That's sufficient. I don't require even to consider the suspension, right? Assuming that suspension does the role of its road holding capability and so on. I am not worried about that stability, that motion of road, that motion of pitch. I am worried only with my vehicle can change its orientation according to the given steering input, and my vehicle I could control the way I wanted. If that is the objective, my so-called yesterday's Newton-Euler equation of very long equation of moment all see is reduced to a simple moment equation. Only one equation sufficient, and the two simple force equations. So this is what is the beauty of your dynamic governing equation for your lateral dynamic study. And in this also further I can simplify. That's what is you see. I require one simple equation, one equation ultimately to say characteristic of vehicle. I will have different brands of vehicle. I'll have different types of vehicle in the sense the hatchback or it's sedan class or SUVs. These are the three groups of vehicle that we call of any of the particular brand. And I have different brands of vehicle. All this vehicle that I have in my hand, I have to talk about its capability of handling. I don't even require these many number of these three equations, which are already further simplified. One simple equation sufficient, that is to look at all these vehicle, how are they executing their steady state motion. So that's one equation itself as lateral dynamics. So to go to that, we look at another two cases. So case 4. So what is case 4 is what is called the pure cornering. So then you may ask, what is then this cornering? These three equations. These three equations again for handling, vehicle handling, for cornering. And you see here Fx. What is Fx is tractive force. So that is varying. If tractive force is varying, that is why you have this equation here. If tractive force is varying, that would have some influence on the vehicle nature. If I have this u dot, what is u dot? It's forward velocity rate, right? U is forward velocity, v is lateral velocity, and this capital U, capital V, we would be changing to small letters soon when you have to look at a ground vehicle, right? These capital U, V, W are there for a space vehicle, any book that you look at for a space vehicle dynamics. And the ground vehicle dynamics are all reputed standard textbooks. If you look at, they do use small letters. Don't get worried about it. You can easily adapt to the notations always, right? So these three equations, I don't even require this Fx. So I say that my U is constant. That means I'm driving my vehicle with the constant speed. That's what is the safe speed we always prefer. And you drive your vehicle on highways, you don't maybe pleasure, no vehicles are there, you accelerate down, decelerate, also on. But we are to go in a traffic flow with the moderate or high speeds so that you will go comfortably, you will also support your other neighboring vehicles. Or you see an automation of your vehicle, traffic control. We say traffic means it's not stagnant, slow speed. All vehicles go in their respective cruising speed so that they can have their relative communication, and that goes. That is what is adaptive cruise control and so on, right? So the speed of the vehicle is constant if I consider in forward direction. And this equation is not necessary. I require only these two equations. So that is what is called a pure cornering. So pure cornering says what U is constant. U is constant. When U is constant, I don't have even Fx equation. I require only two equations, Fy and Mz. So it's very sensible. Fy is what is to have a control of your vehicle when you are doing cornering. You require only lateral acceleration. So you say U is constant, velocity is constant, so acceleration 0. You can't conclude like that. That's conclusion is correct when the motion is only 1D motion. When I go straight motion, I say cornering. Cornering means I'm giving steering input. So when I give a steering input, my motion is 2D motion. The moment the 2D motion is there, I can have the two components of velocities that we have seen in the last class. You see here. All right, here. What is that we have seen here? You see, this velocity can be constant, and you have AT and AN. So AT is 0, but AN is necessary to have the course maintained by the vehicle, and that is what is being taken care by Fy. So you'll have a lateral acceleration, but not the longitudinal acceleration component. That's what is the meaning of this. And then the cornering is called a pure cornering. If this U also is varying, what I mean by that, I do accelerate or brake during cornering, and then I require these three equations. That is case 3, what we have seen now, right? That's case 3. These three equations. And continuing with that, I think you are following me. So I would have only these two equations. So it's going to be M into V dot plus RU, right? Or now you can also write this in vehicle dynamics point of view. Fy is M into V dot plus RU, small letter. So don't get worried. So MZ is IZ is at R dot. So that's going to be the same. M is that. There's no notation change of PQR. So that's IZ is that is only one mass moment of inertia now, because I'm not worried about rotation of vehicle in x-axis and with respect to y-axis. Only orientation change is important for me. So IZ is that into R dot. So R dot is what is yaw acceleration. Yaw acceleration. R is yaw rate. So you know R is R. So this equation is now 2 degree freedom equation. 2 degree of freedom equation. So what are the 2 degrees of freedom? One is this R, what is called yaw rate. Another one is V, what is called the lateral velocity. Right? So lateral velocity is this V dot is there, it's changing. Here U is constant and R is changing. So you have only, these are the 2 degrees of freedom sufficient for to describe your motion under pure cornering when your forward velocity of the vehicle is constant. And what is my the last case is that sufficient case for classification or comparison of your vehicle, and that's called case number 5, steady state cornering. So what I mean by steady state cornering, this is the experiment. So the vehicle, all vehicle, to compare its handling capability, I will do something, a test called a circular test, constant radius test or constant speed test and so on. So you have a circular track, your vehicle will be driven on that with the constant speed, and your lateral acceleration is now fixed for this U squared by R alone. Right? So when U is constant, R is constant, lateral acceleration also is constant, and you don't require the rate of change of the time derivatives are going to be zeros. That means V dot is going to be 0, R dot is going to 1 minute, just a minute, please hold on. R dot is equal to 0. Your equation would be only one equation, Fy is equal to MRV, and M is at equals 0. So these are the steady state governing equation. Yeah, what is the doubt?
Yaw acceleration is also 0, right?
Which acceleration?
Yaw acceleration.
Yeah, that is why it's 0.
Yeah.
MZ is equal to 0. R dot is 0, I have written here. All right. Who is that asking?
Harsh.
Harsh, yeah. Do you follow me?
Yes. No, sir. Actually, you said that yaw acceleration, one time you said it's constant.
Yeah, velocity is constant. Velocity is constant.
Yeah.
So
that's why
here, what do you mean by steady state is the time varying parameters are not going to vary and they are constant. So time varying parameter here are V and R. So they are going to be constant. And you see that these are 0. So your equation here in pure cornering, the term mv dot is going to be 0 and iz r dot is going to be 0. So these two equations for pure cornering deduced by this, and this is the only equation sufficient, and that's going to be a very good equation for to characterize or compare your vehicle handling. So that's the beauty, and that's where we are going to define an important parameter called understeer gradient during steady state cornering. And that understeer gradient is what is sufficient to say which is good vehicle and so on. So that's a classical part of our dynamic lateral dynamics. We are going to look at it, right? Any doubt in this? So for what we discussed? If not, let's move forward now to understand our vehicle model for our lateral dynamics study. That is called bicycle model. I'm going to describe that model, and then an important phenomena, what is called slip angle, and another definition called body slip angle. All know that kinematics of your vehicle model. Vehicle description is what is I'm going to explain you for another 5 to 10 minutes, and then we will go in for deriving the governing equation for pure cornering. So I'm going to now on look at the lateral dynamics of ground vehicle, and that also for pure cornering. I'm not going to take it for steady state. That's a specific case. We will look at it later. Let's go for pure cornering. So there are two governing equations that already I have put it in the previous slide. So when I say pure cornering study of ground vehicle, right, I have to understand an important aspect. So in pure cornering, you have two equations. One is Fy, that's equal to M into V dot plus Ru, and Mz that's equal to Iz R dot, right? So these are the two equations, governing equation. So I have to get this is equal to what? This is your effect force. This is your effect moment. And this is equal to unbalanced forces in lateral direction. So Fy, how does it come in my vehicle is what I have to put. So Fy, how does it come in my this first equation? I require a description of my vehicle model. I'm going to do that now. And similarly, Iz R dot is what is for your yaw motion when you see from the top view. And that's happening because of this moment. How what is that is created in your vehicle on your left hand side is what is that I have to derive. So for that you require what? We require model description. Model description, right? So I'm going to explain you. And before that, let's understand one important definition, what is called the slip angle. So before going into model description, let's understand what is slip angle. Why slip angle is because if this slip angle does not manifested in your tire rod interaction, you will not be able to have this left hand side estimation. So the lateral force is all because of the generation of slip angle. So what is this slip angle, right? So what am I going to do? Instead of looking at vehicle and vehicle model description, time being, I'm going to explain you my tire road interaction of a single tire road interaction when there is a side force acting on the vehicle, how that tire road interaction, that description. First, let us understand to define what is the slip angle. So for that, I'm going to draw this. Let me take this is my ground plane, and this is my front view, and this is my top view below, right? What am I going to draw is I'm going to draw now my section of my tire wheel assembly, which is in contact with the ground. So I have, this is my rim representation. And this is axis of your tire wheel assembly. And this rim, you see, you have your nicely fitted your tire. So the tire wheel rim, if you look at that's a round in shape and torus structure, and you see that I'm going to draw in a particular fashion. So I will be having it something like this, and it is now in contact like this. So this is my section of the tire. The section of the tire all we'll study in detail. I'm not going to explain you what is the section and so on now. So this is contact. So you may wonder that why that is skewed here like this. So this line is now axis of tire wheel assembly. So this plane is parallel to the XZ plane of your vehicle, right? So this is wheel plane, vertical plane. From the ground, normal, the vertical plane. So this axis represents that wheel plane. So this is what is wheel plane. Wheel plane. And you have now this section of your rim. So I have drawn now my tire fitted on this rim on the portion which is now on the ground. On the other side, it will be like this, not distorted. Maybe you will have the tire seated nicely like this, right? And this is the section here. So this is how you will have your tire. So this is at the ground contact, and it's not symmetric, it has come on this side. So if this is that you understood, and this is your rim, and over which I see the section of my tire now, the section of my tire wheel assembly, and this is your ground now. And if I see from the top, my top view of this would be this. So with the same diameter of my tire wheel assembly, I'll have my top view like this, right? And I could say this is this portion, this line if I draw, that is representing my tread of my tire. And this portion is what is this chamfered appearing is what is shoulder and connecting to the sidewall and so on. So this is now in the top view, my tire wheel assembly and its axis. And you see this contact patch now, how that would be appearing in the top view. It would be something like this, skewed, right? So your contact patch would be something coming like that. So this is my contact patch. So if I project this, it will come here. So this contact patch is not in this and it has come here. And on the top, if you see, it won't be, it is symmetrical. As this is rolling and the tire comes and have a contact in the contact patch, it won't get skewed like that. It is skewed like this is all because of the reason there is a side force. So I take the side force here. Let me put that in the other color. The side force. So the side force can be manifested when the tire goes straight, when the vehicle goes straight. The side force acting experience here is maybe because of there's a wind gust acting on your vehicle. There's a side force. So that was pushing your vehicle. So what is happening? This contact also get the wheel goes here, and the contact is not going because it's stuck with your ground. It is in contact with the ground. So you have such kind of deformation. So if that is happening, you have this Fs is what is happening that has to be cancelled. So this force is what is now going to create a force here down, right? You have studied in your rigid body mechanics what is called an equivalent force couple system. So what am I going to do? I'm going to bring this force down and cancel that force. So the system is same. Of course, if I'm not, my intention is not to draw a full free body diagram, just showing some forces at the moment to understand. So this Fs is brought down here, and this Fs here. This is Fs here. So if this system is equal, nothing happened. So this balances, I have this. And these two are of same magnitude and opposite sense, acting, creating a couple. And that couple makes your tire wheel getting a pressure on the hub, right? So when side force is acting, the tire wheel assembly get a pressure on your axle hub. So that's a necessary couple. And in the top, if you look at this Fs would be here now along this. I just have brought down to the ground. So you'll see in the top view like this. I don't show this couple now for a convenient here. And rather you see this Fs now to balance, which is there here. The balancing force is not on line. It is in offset to this. So somewhere here exaggerated. So this is my Fy. So this Fy is what is balancing. And this would act at a distance from here called TP. That is called pneumatic train. pneumatic trail, right? So this pneumatic trail is an offset distance of your resultant Fi in the contact patch, which should balance this force. But what is happening? It's not force is balanced, but you see there is an unbalanced couple. So this M is that would be facilitated by this Fy into Tp. So this moment is what is called the self-aligning torque. Self-aligning torque. So the self-aligning torque, why? Because what is going to happen now is that force is coming here, this aligning torque is because see this distortion of your contact patch. So this distortion of your contact patch will take initially the vehicle which is going rolling straight. It's the wheel plane heading in this X direction, in this direction, but now that's going to be with some angle, it's exaggerated angle. So this is your wheel plane in the top view. And this angle is what is alpha. So this contact patch, the direction of your wheel plane motion is not in this, it's an angle appearing, and that angle is what is called the slip angle. So the slip angle will manifest when there is a side force. When there is no side force, this angle won't be there. So you'll have the wheel plane is in this forward direction alone. So this angle is exaggerated. It's very small angle. Small angle, right? I'm just showing it as an exaggerated angle of 45 degrees for you to understand. That's all. So this is what is called a slip angle. So the slip angle is what is manifesting the creation of your Fy here. So when I say that, you should look at the variation of this Fy is going to be function of the slip angle. So if I look at that, it will be non-linearly varying, and it is going to have some asymptotically meeting some limiting value, and that limiting value is given by road adhesion limiting value. Please mute your system. So road adhesion limiting value. So that is MEP times W. That's what is going to be a limiting factor here, right? So road adhesion limit. That's what is going to dictate. So this will not go ever increasing. It will be. And this slip angle also will not go ever increasing. So we would be having it some desirable value of slip angle only. We'll understand that all when we do our tire dynamics separately. Right. So this. So you may also have, I'll draw another curve. Why do I draw this? Is because there are two kinds of tire. One is called a radial tire. Another one is called bias tire. So this one upper is for radial tire, and this one is for bias ply tire. So we'll see the classification. That's all separately tire dynamics module. At the time being, you see this, and here is where I am defining the slope. The slope here gives me an important property of tire called the lateral stiffness of the tire or cornering stiffness of the tire. So how do I define this lateral stiffness? This is lateral stiffness or cornering stiffness of the tire. So you should understand this cornering stiffness is not similar to radial stiffness. Radial stiffness in your quarter car model you have studied. That stiffness of the tire is what is called the radial stiffness of the tire. And that is to account what is the elastic force that are coming into your quarter car model. And here, cornering stiffness is necessary for your Fy. So how now this cornering stiffness is defined? That's variation of this Fy, dou Fy by dou alpha. So I use here dou symbol, partial symbol, because there are other angle called the camber angle, Castro angle, and so on associated with that. And they are all assumed to be not considered. And I consider only this alpha. When alpha is 0, what is the slope of this curve is what is defining my cornering stiffness. If I take this cornering stiffness constant, my tire is considered to be a linear model for study, right? If I consider my cornering stiffness is varying as it is like that, the slope is keep varying, then it is non-linear tire model. So in reality, in your vehicle dynamics study, you would have that as a non-linear tire model. That's what is Hans Pajeka model, or even very old Julian's model of your tire and so on. You study, you will understand that all we are going to study separately of tire models required for your vehicle dynamic studies, separate module. But at the time being, I have to explain you because unless and until you understand how this FI is manifested, this FI at CG in your vehicle, how does it come? It's because of FI generated at your tire road interaction. And how this FI comes is because of the phenomena of slip angle. This phenomena of slip angle would occur whenever there is a side force acting. And along with that, you are able to define now your, so this Fy would be C alpha times this alpha. That's a value of Fy. So as this alpha increases and this C alpha is constant, you would have this variation. That variation goes like this linearly in the model, right? And you define your cornering stiffness in this fashion. So what is the angle that I'm talking here is not going more. So maybe till here 16 degrees max. So maybe 2, 4, 6, 8, 10, 12, 14, 16. So at that time itself, it is reaching to this. So you don't expect the slip angle to go more, right? So this 16 degrees here, it's appearing to be 45 degrees. Don't worry. I just have put it for you to follow that. That's all. Any doubt here? So there are two couples that we are seeing here in this diagram. One is the couple in this plane. This plane is what? Vertical axis and this. So it is your Y is that plane. There is a couple. That couple is giving a pressure of your pressure of the tire wheel assembly on the hub. And there is another couple that is on the ground contact, and that is what is manifesting your aligning, self-aligning torque. So as this heading direction is going at an angle, the tire wheel, the wheel plane of your wheel would be trying to align with this. That is why it's called an aligning torque, and that is manifested by this. And the resultant of Fy will not be in line with the Fs. It will be with an offset behind it. That's why it's called a trail. Pneumatic trail. So this pneumatic trail all is coming because of the very much important property of your tire viscoelasticity and its typical deformation phenomena, or the tire getting adhered to the ground as well as sliding in the ground simultaneously. It's not fully sliding. It is part of the tire contact patch in sliding and part of the tire patch is in slipping out. So that is interesting physics that we will see separately later on. And that is what is manifesting this Fy comes in this rear, and that is giving you a self-aligning torque. That's why word self-aligning torque. So you could experience that you take a corner and then leave the steering. You feel that steering wheel comes back. That means what? You are giving an input. You are giving an orientation change of your tire wheel assembly, and then you leave it. The tire comes back again, aligning with your vehicle forward direction, and that is what is called a self-aligning torque, and that is manifested because of Fy, which is generated when you do a corner, and then you leave it, and that Fy and to TP is what is trying to make it, and then they get aligned. And self-aligning torque, an important manifestation of moment, that's important. Right, so this is all some of the physics of tire rod interaction that you see, where you define your slip angle for your vehicle dynamics, right? Fy to get generated. So now with this understanding, I'll stop at this point of time, and then we will go for model description and then pure cornering equation. How can we derive? And how are you going to represent that governing equation 1 and 2, which is of 2-degree freedom model called bicycle model. We'll understand why is it called bicycle model all in the next class, and its kinematics and its actual dynamic equation governing and its convenient form representation called the state space form. All is what in the next class I'm going to teach you. So that now I just stop this lecture stating to summarize what we did today. So we essentially understood how can we make use of the Newton-Euler equation derived for a vehicle in space for a ground vehicle. So what are the sensible, necessary assumption that would correlate with the real physics of your vehicle during drive is what we have understood. There are two with respect to geometrical aspect of your vehicle, symmetricity, principal axis, and so on. Another thing is the necessary elimination of degrees of freedom. Like in ground vehicle, heave motion and pitch motion can be eliminated first to go, and then you can also eliminate your roll motion as you look at only directional control and stability in yaw plane. So your equations reduce 3 are further reduced to pure cornering only by 2. And even in this pure cornering, if you look at that motion, a steady state motion, that the time varying parameters, the lateral velocity and yaw velocity are constant, then you see this is going to be only one equation. That's quite sufficient equation for comparison of your vehicles for its handling capability. So with that note, we were just understood an important physics of the slip angle generation at the contact patch, and then that is what is responsible for your variation in Fy. So Fy is going to be because of slip angle, and you get your Fy because you multiply slip angle with your tire cornering stiffness, and the tire cornering stiffness is defined by the variation of Fy as function of alpha if you have, and by this slope when alpha is equal to 0. And this partial derivative is because I don't consider simultaneously camber angle here, right? So with that all, I stop this lecture, and tomorrow we'll go on with looking at the vehicle model reduced to real vehicle, how is it being considered as bicycle model, and associated kinematics and geometrical aspects in it, the vehicle parameter, and then let us derive this two equations, governing equations, means on the left hand side parts, and then comfortably represent them as a state space form to go further in our lateral dynamic studies. So I stop at this point of time. If you have any doubts, please do ask. Otherwise, I will end the lecture. Do you have any doubts?
Last time I asked you about what was the class average. Were you able to find that
One
out?
minute. Just let me stop recording.